Okay, so this unit is called the universe, unit 6. And again, this is for separate science only. So if you're doing double awards, you don't need to be watching this or using this presentation. This is for separate science only. So in this, we're going to look at basically how we've observed the universe. So we're talking about absorption spectra and how we can use them to identify the gas. We're going to talk about emission spectra as well because it helps us understand that. We're talking about how we use them basically to tell us what stars and planets and things are made of. We're going to talk about cosmological redshift, a little bit about Edwin Hubble. We're going to talk about the cmbr, and then we're going to talk about the Big Bang Theory. So that's what this presentation is about. So again, hopefully you know the drill by now. Here is a bunch of helpful links. If you're watching this on YouTube, they're in the description below. If you're watching this as a presentation, they're in, you can just click them, can't you? Okay, so emission spectra. Now, strictly speaking, emission spectra are not on the spec. But I don't think you can understand absorption spectra without understanding what emission spectra are first. So you will have learnt in chemistry that we have electrons in orbits or shells around our atom, which is a better idea. The word orbit there is not strictly true, but anyway. And hopefully you might have discussed things like flame colours, because that's basically an emission spectra. A flame colour and emission spectra are exactly the same thing. So when an atom absorbs energy, these electrons can jump up to higher shells. Okay. Now, how can they absorb energy in case of a flame colour? That's through the heat of the flame. Could be through electricity as well. It's how neon lights work. Now, after time, these electrons relax because they don't like being in that higher energy level. They want to get back down to the ground level, to where they started. And when they do, they release that energy they absorbed as light. And the wavelength, or the colour of that light, is specific to an energy gap. Okay, and this is why each element has its own flame colour, because each element has different emission spectrum. We can use that if we've got a solid sample. We obviously can use that to identify an element, and this is what scientists have done on Earth. So we can try different elements and we can see their emission spectra. Now, absorption spectra basically are the opposite way round. So if you shine the right coloured light on a sample or gaseous sample of the material, then what will happen is that electron will absorb that colour of light and get promoted up to a higher energy level. Now, if you were looking straight through the sample, that light will then be missing. So you'll see it, if you pass white light through the sample, you'll see the missing light, the light's been absorbed as black lines. And this is our absorption spectra. And basically, if you take the emission spectra of an element and the absorption spectra of an element and overlay them, you'll just get a continuous spectrum of light. Okay, because they are exactly the same. Now, well, how do we use absorption spectra? Well, if we look at the light from stars or from a galaxy or going through a planet's atmosphere, then we can see these absorption lines, and because they're very specific to each element, we can then tell what elements are present in that star, galaxy, or planet's atmosphere, and that's how we use them. Now, there was one issue with this. When the scientists overlaid these patterns, they noticed that there were the right number of lines and they were roughly in the right position, but they appeared at too long a wavelength. They appeared at redder wavelengths. And they thought about what's called the Doppler effect on Earth, that when an object is emitting a wave and is moving towards you, that wave gets squashed. When that object is moving away from you, that wave gets stretched. And they assumed it was the same idea as this. So they concluded that basically, when things appear redder, the object must be moving away from the observer. And what this means is that basically, or what happened is, because the object and the observer were moving away from each other, the space in between them had stretching the wavelengths of light out. Okay, and it's quite important that that these wavelengths of light appear red, because it's the space between the objects that has got bigger, not just them moving away from each other. And this is where we get the idea of an expansion in space. Now, Edwin Hubble, most people have heard of Hubble because of the Hubble telescope. That was nothing actually to do with him, just named after him. And so basically what the Hubble telescope is the space telescope. And what it's named after Edwin Hubble, like I said. What Hubble did was he was the first astronomer really to go, there's stuff outside our galaxy out there. The other thing he noticed was that when he looked at different galaxies, the further away that galaxy was, the more redshifted its light appeared. And so what he did was he basically went, well, if I plot the speed at which they're moving, or how redshifted the light versus how far away they are, he got a graph. And he got this straight line that seemed to go through the origin. And so what he went, well, if I play this in reverse, so none of these galaxies are moving, they appear to all start from a similar point. And this was the start of the Big Bang Theory. So the idea is cosmological redshift. If you play it in reverse, all the galaxies appear to start from the same point. Now, the one problem at that point they had with the Big Bang Theory, this idea that everything had started from one point, it was like, well, everything must have been really hot, it must have been a lot of energy around, but you couldn't see it. We couldn't see this radiation in space. However, what scientists found out was basically after World War II, hopefully you understand World War II, there were massive advances in radar and microwave detection. And so there was an awful lot of microwave detectors pretty much just lying around after World War II. So scientists got hold of them and went, well, where else can we point these things? So they decided to point them at the night sky because they knew there were some microwave transmissions coming in from the night sky. And the story goes that basically the scientists who were working on this kept pointing it everywhere in the night sky, and they basically kept getting this noise, and they thought there was a problem with their machine, and they did loads of stuff. It's in one of the videos linked at the beginning of this presentation. Have a look at it, including they thought it might well be pigeon poo, because pigeons had taken up sleeping in their detector, so that might be it. But anyway, eventually what they discovered was no, this is actually a signal from the sky. And this was the leftover radiation that basically over billions of years, due to cosmological redshift, had been stretched from the gamma rays to what it was to now microwaves. So what they called this was the cosmic microwave background radiation, because that's basically what it was, background radiation in the microwave region, or cmbr for short. And cmbr is fine, you can use cmbr and everyone knows what you're talking about. Now, cmbr was the second piece of evidence needed for the Big Bang Theory. So now we've got the fact that everything appears to be moving away from a single point, and we found the radiation, this leftover energy from this point when everything was really close together and was really hot. And so that's where we got our Big Bang Theory from. Okay, so over to you then. Question time for you. If you click the document, if you've got this on PowerPoint, remember stop the presentation. You can double click on the document and the PDF should appear. If you're on YouTube, there'll be a link to it in the description below. When you've done the questions, restart the presentation, restart the video, and I'll go through the answers on the next slide. Okay, so now we're going to look at the questions from the universe topic, which is only for separate science. There haven't been many of these questions asked on the new one yet, so we've only got 3 pages to do, so we'll go through these dead quick. Okay, so we're starting with Foundation 2018. So Foundation 2018, and this was the first question, so let's get the right one open. Okay, so the light from distant galaxies has changed to travel through the universe. The wavelength of light from distant galaxies has decreased. No, they generally have got bigger. We want 3 boxes as well. Distant galaxies look red. No, not necessarily. The absorption spectra from distant galaxies generally are now redshifted. Yes, that's correct. The universe has expanded. That's correct. Light received from our sun is shifted to the blue end of the spectrum. That's not correct. And the sun's absorption will show no redshift, it's not moving towards or away from us. Name the model of the universe that's supported by cosmological redshift. That's the Big Bang theory. Just Big Bang would do, but let's put it all in there. Right, good. So 4 marks, move on. Okay, so we're now 2019 and question 1. Okay, so place a tick next to the 3 correct statements. The dark lines in the spectra of distant galaxies are blue shifted. No. Further away a galaxy is, the longer the wavelength of the dark lines. That's generally true. Dark lines in a spectra are green shifted, not a thing. Dark lines can be used to identify. That's correct. The dark lines in the spectra of distant galaxies are red shifted. Fine. And the shorter the wavelength, no, that's wrong. So it's those 3. The shift in absorption lines provides evidence for the Big Bang. State the other piece. As we've just seen on the last one, that's cosmo. Oh no, we've got cosmological redshift. That's what we're on here. Sorry, the other piece data is the cmbr. So the cosmic microwave background radiation, cmbr. Okay, and then we've got our last question on this, which is about explain how cmbr and cosmological redshift provide evidence for the origins of the universe. So both support the Big Bang theory. That the universe started from a single point. Okay, and then so we've got to talk about cmbr first. So then cmbr. So this is going to be high energy from the start. Let's phrase that slightly better. High energy produced at the Big Bang has so that's what it is. High energy waves, it's be even better, produced at the start of the Big Bang
over time as universe has expanded, these waves have redshifted to microwaves. Okay, and the other thing about the cmbr appears to have uniform density in all directions. Okay, and when we talk about redshift, cosmological redshift, okay, and this is evidence for expansion. Since radiation was emitted. Okay, not quite enough there yet to hit all the marking points, as space between galaxies has stretched. Any light has also been stretched. Increasing its wavelength. Okay, so key things on this. cmbr is basically high energy electromagnetic waves or high energy waves produced at the time of the Big Bang. Over time, as the universe has expanded, they've been redshifted to microwaves. And the other thing about the cmbr, if you look anywhere in the universe, it seems to have a uniform density. So there doesn't seem to be a point where that radiation is concentrated. Okay, and then for the redshift, well, it's evidence of the expansion, and it's basically that as the space between the galaxies has stretched, expanded, any light in that will also have been stretched. Okay, so let's just make sure the bottom of that's on there. Let's get it all on there like so. All right, so well done for making it this far. Okay, and on to radioactivity now.
Okay, so well done for making it to the end. Thanks for watching it. I know some of these are pretty long. And like I said, if they help, leave us a comment. If they don't help, leave a comment. If you'd rather the review bits, which make them really long, I'll put in separate videos. Again, let me know. It's not a difficult job to do, and I can put them in separate videos rather than putting them in the main video, and it will make basically 2 shorter videos. Please like, please subscribe, and hopefully they help with your qualifications.